Okay, so Unit 9, Objective 4, Scale Factors. So in our Pearson book, this is actually 10.3. So for Pearson, it's actually Chapter 10, Objective 3, which starts on page 755. So in our textbook, though, it is Pearson Chapter 10, Objective 3, which is on page 755. So what we're going to learn here is about scale factors. So we're trying to, a lot of what we're doing is geometric modeling. So what's happening with the volumes, areas, and relationships, so how does everything apply? So we have done already, our density volume problems, which had to do with three-dimensional objects, and then we're looking again here at what's relationships between our one-dimensional, two-dimensional, and three-dimensional objects. So just to kind of clarify, make sure we're all kind of on the same page and we understand what does it mean when we talk about the different dimensions. So when we talk about something being one-dimensional, most people think of it as just the top two here, like linear, length, height, base. Like they think of all of those things as being one-dimensional. But perimeter and circumference is also one-dimensional because it is a linear measurement, right? When we talk about perimeter, we are talking about like the distance around, which is a linear measurement. And I get that it's creating a two-dimensional object, but that actual distance around is a linear measurement. And so that's perimeter and circumference as well. So how do we know we have a one-dimensional object? We can look at the unit. So it's centimeters, inches, feet. So anything along that, those are units of linear measurement that are one-dimensional. So two-dimensional objects refer to our area or even our surface area. And so even when we talk about surface area, so if I draw a cube here, for example, and I want to know the surface area, it looks like I have a three-dimensional object, which I do. But when I'm talking about the outside value, so if I want to know what's the area of that face or the area of this face, I'm still talking about the two-dimensional piece, like the wrapping around a three-dimensional object. But that wrapping around is a surface area, so it is two-dimensional. And how can I tell by the units that I have something that's two-dimensional? Is that they would be square units. So meters squared, centimeters squared, feet squared. So if it's two-dimensional, it should be a unit measure of power of 2. One-dimensional should be a unit measure of power of 1. So then three-dimensional refers to just our volume, so if we fill a can with liquid, we are creating volume, right? If we talk about the solid itself, we are talking about volume. And how can I tell I have three-dimensional by units? Is I can look at the power. If it's cubic meters, feet cubed, gallons, liters, these are all measurements of volume. So three-dimensional should have a power of 3, or if we're referring to liquids, gallons or liters. Okay. And so each of these have a proportion if the figures are similar. So last year you studied similar triangles, similar figures. And we talk about if they're similar, that means they're proportional. So if I look at something right here, and I want to say, okay, if these two figures, so if this is a square, so we use a notation like this just to remind you, that means these two sides are congruent, right? So this is a square. I don't have a right angle in there, but let me pop that in. And if I look at this and I say this figure is similar, then that makes this one be a square as well. So this side would be congruent to that side. So I have two squares here, and I want to say, well, what is the scale factor between these two, or how are they proportional? So the scale factor for this, so I'm just going to use SF for scale factor, would be 2 to 5. And there's lots of different ways to write that, so a fraction is okay. You can also use a colon in between, right? And you can even use the word 2. Okay, and so all of that means I have a scale factor of 2 to 5, or that these two squares are proportional to each other. So meaning this square is 2/5 the size of this square. Okay, so 2 to 5. So if I asked for, well, what is their height scale factor? It would also be 2 to 5. If I asked for the perimeter, right, the perimeter scale factor, it would also be 2 to 5. So even though the perimeter here is 8, right, because 4 sides around, and the perimeter here would be 5, 10, 15, 20, I could say, okay, the perimeter has a scale factor of 8 to 20, which is true, but if I divide the 4 out, I would get 2 to 5 again. So regardless of being perimeter, regardless of comparing their base or their height, because they are proportional, they would have the same scale factor of 2 to 5. So let's take a look at their area. So if I want to find the scale factor of their area, I need to know what their area is. So if this is a square again, so this is the same as this over here, I just have the inside shaded. The area of this square would be 2 times 2, which is 4. The area of this would be 5 times 5, which is 25. Okay. So its scale factor would be 4 to 25. Okay. Okay, and then finally if I look at their volume, so I find the volume of this cube, so this is a cube, so all measures are the same. So this volume, I would multiply, find the area of the base, so that would be 4, times the height, which would be 8. Area of the base would be 25, oops, times its height would be 125. Okay. So then the scale factor between their volumes would be 8 to 125. Okay, so I calculated each of those by finding the areas, by finding the volumes, but I didn't need to do that because there is a relationship between one-dimensional, two-dimensional, and three-dimensional. So if I know the scale factor of any of the 3 dimensions, that means I automatically know the scale factors of the other 2. So if I know the scale factor of the linear measure or the one dimension is 2 to 5, then its scale factor for the area is the same but times itself. So if this is 2 to 5, then this would be 2/5 times 2/5, so 4 over 25. So if I know this scale factor is 2/5 for the area scale factor, it would be 2 over 5 and then squared. So 2 squared is 4, 5 squared is 25. And it doesn't have to be a square. It could be for any object that is similar to the other object. So then same thing here. If I know its linear scale factor for one-dimensional, that means I could figure out its three-dimensional. So for the three-dimensional object, I could do the same thing. So for the volume scale factor, it would be 2 over 5, but because now we're talking about volume, which is three-dimensional, right? Volume is three-dimensional, then I would raise this to a power of 3, and that's how I'm getting 2 cubed is 8, 5 cubed is 125. So although I could take the time to calculate the volumes, I don't need to if I know any of the scale factors. Okay, so let's go ahead and take a look at 2 examples. So we're going to do questions 3 and 4 off of the worksheet. Okay. All right, so before I do any scale factor problems or proportional problems, I always want to write down what are my one-dimensional, two-dimensional, three-dimensional scale factors. So I'm going to do that on this side over here. So I'm just going to do 1D for one-dimensional scale factor, which is our linear measurement, 2D, which is our two-dimensional scale factor or area, and then 3D or three-dimensional, which is our volume scale factor. So they give me the heights here are 20 and 30, and they are telling me that the pictures are similar to each other, so they're proportional. So then I know that the height of the smaller is 20 and of the larger is 30. So it has a one-dimensional scale factor of 2/3. So then its two-dimensional scale factor is just that times itself. So it's two-dimensional, so that would be squared. So 2 squared is 4, and 3 squared is 9. So its two-dimensional scale factor would be 4/9. So for example, if I knew that to paint this, it took, 3 square meters of paint, then I would know that this is proportional, right? So this would be, 3 square meters of paint to whatever this would be, so that they would stay 4:9 proportion, okay? And then for my three-dimensional, that means I would take my one-dimensional and I would cube it. So 2 cubed is 8, and 3 cubes is 27, okay? All right, so then I'm going to go ahead and read the question here. So it says the two pictures are similar. We knew that, and so that allowed us to create our scale factors. And the volume of the smaller pitcher is 8 cups. And they want me to find the volume of the larger. Okay. So because we're talking about volume, then that means we want to use our three-dimensional scale factor, which is 8/27. And so I'm going to use that proportion to find the volume of the large. So the volume of the small is 8 cups, and I don't know the volume of the large. So I can actually just look at this and say, okay, if these are equal to each other, and I know that the scale factor is 8/27, then if there's 8 cups here, there has to be 27 cups for the volume of the large. So the volume of the large pitcher would be 27 cups. And I can solve that algebraically, but I don't need to, right? I could just kind of reason through that. Okay, and then question number 4, so this is our last one. Okay, so the figure to the right is of 2 shampoo bottles that are mathematically similar, so they are proportional to each other. So that means I'm going to go ahead and set up my dimensions. So I'm going to compare linear measurements, so 18/27. And I could divide a 9 out of both of those. So the one-dimensional scale factor is 2/3. So two-dimensional means I need to square that. So 2 squared over 3 squared. And then three-dimensional scale factor means I need to cube that. So 2 cubed over 3 cubed. Okay. And it says that the cost of the shampoo depends only on the volume of the liquid in the bottle. And if the small one costs, so the volume of the small costs $3, what should the large one cost? So it depends on its volume. So I'm going to write V for volume even though we're talking about cost. So that means I need to use my three-dimensional scale factor because I'm referring to volume. So the volume of the smaller one was $3, so that's my top value. And I don't know the cost for the larger one, so I need to find the volume of the larger one. And so it is proportional. So then from here, I just need to solve. So I want to multiply both sides by my denominator. So I want to multiply by 27V. And there's more than one way to solve this. I know you all have your different ways to do that. So then when I multiply by 27V, the 27's cancel. So I have 8 times V. And the V's cancel. And then I have 3 times 27, which is 81. And then to get V by itself, I'm going to divide both sides by 8. So the volume of the larger one, which also equates to the cost, is just 81 divided by 8, which is $10, and I'm going to round up to 13 cents. And that's 9.4.